Okay. All right. So we're talking MCMC for. Oh yeah. Do we want attendance? All right. Give me a second. All right. So we're doing. What we're talking about is MCMC for multivariate distributions. Yeah. And then on Monday we talked about. So on Monday, what we covered was the Metropolis, kind of the multivariate version of Metropolis, right? Multivariate Metropolis Hastings algorithm. But again, if you just have a symmetric distribution, it's just the Metropolis algorithm, symmetric proposal. And what this requires is it requires that the proposal distribution to be multivariate. Okay. So, and we said, examples of multivariate were, we had the multivariate Gaussian, which we're familiar with. We also have, multivariate kind of uniform, and so on and so forth, right? So it requires the proposal distribution to be multivariate. So examples are multivariate Gaussian, or multivariate uniform, etc. Right. But there are some issues, okay? Issues are that with higher dimensionality, fewer of our values that are proposed will be accepted. Okay. And so, sometimes we run into chains that get stuck at certain values, or we shrink down our proposal to be so small that our chain explores the space very slowly. Okay, so our chain might get, quote, stuck at certain values, or we shrink our proposal distribution so much that the chain, kind of explores the space very slowly. If we had infinite time and infinite computational resources, this isn't an issue, because the MCMC theory says that in the long run, towards infinity, the stationary distribution matches the target distribution, so you're fine, okay? But we don't live in the land of theory with infinite time, so these problems where our chains do get stuck and our chains are inefficient, these are issues for us, okay? So the Metropolis algorithm, Metropolis Hastings algorithm, does work in the multivariate situation, but it can lead to having an inefficient chain, which can be a problem in the real world. Okay, so today we're going to take a look at the Gibbs Sampler. All right. Okay. So the Gibbs Sampler, much like the Metropolis algorithm, is a MC method, okay, Markov chain, Monte Carlo method that in the long run will give us a sample that is representative of our target distribution, okay? So Gibbs Sampler, this is another MC method, okay? Which means, you know, in the long run, will give us a sample that is representative of the target distribution. Okay. And again, just so we don't lose sight of the big picture, is that, you know, if we're able to sample from the target distribution directly, then great, we should do that. But there are many situations where we can't. And so, well, first of all, if we can analyze the target distribution directly with math, we should do that. And if we can't, then we try to get a representative sample from the target distribution by sampling from it directly. And if we can't do that, then we might use an MC method where, you know, we start at some arbitrary location and try to move around until we find the target space, okay, and then sample, right? Ideally, if we could start in near the target space of high probability, we would do that. But, you know, sometimes you have no idea, and so you just start off in a bad location. And our MC methods say, you know, eventually we'll find the right spots. Okay. So so how does the Gibbs Sampler differ from the Metropolis Hastings algorithm? Okay. Well, the Gibbs Sampler, basically the idea here is you've got a multivariate distribution that is difficult to sample from, but maybe you can break it down to a bunch of univariate distributions that we are able to sample from. Okay, so this is kind of the big idea of Gibbs sampling. Is you know, there is so the Gibbs sampling only applies for multivariate situations. We would not, it doesn't exist for a univariate scenario. Okay, so there is a target distribution, target multivariate distribution. That is difficult to sample from directly. Okay. So instead, you know, it does require some math. Okay, so the Metropolis algorithm, the advantage of that is it doesn't really require any math. You just need to know your target PDF, or at least something proportional to the target PDF, and then you have this completely unrelated proposal distribution, and you just keep proposing, and then you just test it out. Okay. So with Gibbs sampling, it does require some math, and you know, we do need to do some math. We do some math to kind of break down the multivariate distribution into a bunch of univariate conditional distributions. Okay, and then once we've broken them down into a bunch of single variable conditional distributions, we will sample from the univariate distributions. Okay, and then we will then sample from the univariate conditional distributions. Okay, so it might be like, you have your target distribution is multivariate. It's got 7 variables altogether. Okay, we say, well, it's difficult to propose a value across all 7 variables. So instead, we'll break it apart into 7 univariate distributions. Okay, but because these variables could be related, they've got to be conditional. And so we break them down into univariate distributions. We have a lot of methods for drawing samples from univariate univariate distributions. So what we'll do is we'll just go through and we'll sample sample from each univariate distribution. And there's a few ways. There's random. I forget what these. I gotta look up how we call them. We call these the random scan and the systematic scan samplers. Okay, so there's kind of two ways of sampling. Okay, we can select a univariate distribution randomly. Select, I'll say, one of the univariate distributions randomly. Okay, get a value. Okay, and then select another distribution, etc., etc. Okay, or we can go select each distribution systematically. Select a univariate distribution one at a time. Distribution. Okay. Do you guys remember coordinate descent for optimization? It's kind of like that, except it's for random sampling. Okay? And so the way it works is you have a target distribution that's multivariate, and then you have to do some math, but basically you are going to say, what if I set all of the other values in our multivariate distribution to be constants, and now I'm just going to sample for one of these things. Okay, so let me pull up the picture, because the picture perhaps is better, and I would try to draw the same picture, but my picture would look terrible. Okay, so here is the picture that I want. Okay, so the mesh grid represents a 2-dimensional target distribution. Okay, so the blue mesh grid represents our target multivariate distribution. Okay, in this case it's P of theta 1, theta 2. So this is our target distribution. You know, it says it's a posterior, so it might be P of theta 1, theta 2 given our data. Okay, but basically this is what it is. Okay, and we're going to say, you know, maybe it's difficult to generate a value, a random value for both theta 1 and theta 2 at the same time. Okay, so we'll say, you know, it's difficult to randomly sample theta 1 and theta 2 at the same time. So just to generate a value here, okay? So what we've done here is in this picture, we kind of set theta 2 equal to, you know, a constant value. Okay, so we lock in theta 2, and what that does is it effectively creates a slice from our multivariate distribution. Okay, so we set theta 2 equal to a constant, and so now with theta 2 quote locked in, okay, we have a slice of the multivariate distribution. Okay, and the slice is univariate. Okay, so basically we have now, so the slice is basically probability of theta 1 given that theta 2 is equal to some value. Is there a notation for this? Yeah, just theta 2 is equal to, we'll just say theta 2 at super time t. Okay, so this is, so theta 2 is set to be equal to the theta 2 value at time t. Okay, and so we can see that. So this represents a slice, and from this now univariate distribution, we draw a random value for theta 1. Okay, and so from the slice, we draw a random value. Okay, and so this will be, we'll say theta 1 at time t plus 1. So our next value of theta 1 will come from our slice. So we condition the multivariate distribution on the other variables to reduce it down to a unidimensional distribution, and we draw a slice there, and we draw a random value. Is that okay? All right, and we would do the same if we have you know, a random distribution of 7 variables. We would lock 6 of them in place, and now we're down to a distribution of just 1 variable. Okay, so so we have drawn this value. This is the value for theta 1. So this is this dot represents our random theta 1. Okay, and so now we lock that value in, and this is our next picture. Okay, Okay, so we have now drawn a theta 1 value, and we will lock that in, okay? So we have drawn theta 1 at time t plus 1 from the theta 1 at theta 2 at time t, okay? We have drawn this, okay? So we, quote, lock in that value. Okay, and so our distribution of our multivariate distribution over theta 1 and theta 2 becomes probability of theta 2 given theta 1 is now equal to this value. Okay, so we do that, and then we repeat this process. Okay, so now that we have a conditional distribution, okay, we draw theta 2 from this conditional distribution. And so we get theta 2 at time t plus 1 to be drawn from this distribution. Okay, and then so now we combine those, and so we have successfully gone from theta 1 comma theta 2 at time t to our next value, theta 1 at time t plus 1 and theta 2 at time t plus 1, okay? And it would go continue on. So in this case, this would be with when it's two variables, I think a systematic sweep makes sense. Systematic in this case would be you do one variable, randomly sample it. Now that you've drawn that value, you randomly sample from the other way. Okay, so it's kind of like coordinate descent, except in coordinate descent we weren't randomly sampling, we were finding the minimum, and then we would condition the multivariate function on that value, and then we would find the minimum of the other variable, and we would condition the multivariate. And every time we're conditioning the multivariate thing to become a univariate thing. Okay, and it's something similar, except we're using it for the process of generating a random sample. So we're not trying to maximize or minimize anything. We we condition our distribution so that they become univariate, and then we randomly draw the values from that conditional distribution. Right. So the hard part is sometimes doing the math to figure out what this univariate conditional distribution looks like. Okay. I think in the example we've done so far was basically on Monday we looked at flipping two coins. Okay, and in that example it's kind of silly because the two coins are independent, and so even if you like condition on one, the other one's not really affected. But I mean we can we can do the math and just kind of see, and you can see the math can get a little bit messy. But well, I don't know. Maybe I've got another example. Okay. Here, let me formally write out the the Gibbs Sampler algorithm. Okay, so first we'll do a systematic scan Gibbs Sampler. Okay, and I would say systematic scan, this is probably like your default Gibbs Sampler. So if somebody talks about Gibbs Sampler and they don't say like I'm talking systematic scan or random scan, they probably mean systematic scan. This is kind of the normal, the regular Gibbs Sampler. Okay. So our goal here is to generate, a sequence of. I know in the example, I'm gonna switch it. I'm gonna just say a sequence of x's. Okay, generate a sequence of x. Okay, so in the example I used theta. Okay, and it's a sequence of x's, and I've got a arrow to indicate that this is multivariate, right? So sequence of x coming from our target distribution. Okay, and so we'll say let x at time t be just some sequence of x1 at time t, x2 at time t, so on and so forth, up to xd of time t. So target distribution is d dimensions. So we have this, okay? And then, so at time t plus 1, okay, what we do is for each I equal to 1, 2, ... d, basically we generate xi at time t plus 1 from your distribution p of x sub I given everything else. So you've got x1 at time t plus 1, x2 at time t plus 1, all the way up to xi minus 1 at time t plus 1, and then xi plus 1 at time t, all the way up to xd at time t. Okay, this looks a lot crazier than it is. Okay, the idea is, so this is the entire algorithm. But let me just kind of do an example for d equals 4. Okay, if we have 4 dimensions, then what we do is we have x at time t is equal to x1 at time t, x2 at time t, x3 at time t, and x4 at time t. Okay, so that's our x vector. And then basically x1 at time t plus 1 is going to be randomly sampled from we condition on the other 3 variables. We have x2 set to x2 at time t, x3 set to x3 at time t, and x4 set to x4 at time t. Okay, and we randomly sample x1 the next value of x1 from this conditional distribution. Once I've drawn that value of x1, I will use that to get my next value x2. Okay, so once I have drawn x1, we use that to get x2. So what this will look like is that we are going to draw x2 coming from the conditional distribution where it's just of x2, and we've conditioned and we set x1 equal to x1 at time t plus 1, the value that we just drew, and then the other values still have not yet been updated. Let me just I'm just cleaning this up to make my print, I don't know if that's any prettier. Okay, so this is the value we just drew, and then the other values still have not yet been drawn, so we're still using the old values from the previous iteration. Okay, so we use the value that we just drew. This is kind of like my brand new value. Okay, and then we'll get a brand new value for x2 at time t plus 1. Okay, and then now that I get a new value for x2 at time t plus 1, then I use that. Okay, and then I'll draw x3, and it'll be x3 conditioned at x1 at time t plus 1, x2 at time t plus 1, and then the only thing that will be left over will be x4, and x4 will still be using the old values. Okay, and then you sweep through all 4 variables one at a time, conditioning on the other 3, and you're going to use basically the newest values that you have for each of them. Okay, and so if you just drew new values during this iteration, you'll use them, and if you haven't gotten to those variables yet, you'll use the values from the previous iteration. Okay, and you just cycle through, you go through all 4 variables, and then you've got now a new coordinate in 4 dimensions. Okay, and then next iteration you want to get another multivariate thing. Yes?
Is there an advantage to not doing it systematically and doing it randomly? Random scan, or is not really allowed?
Is there an advantage? I guess it depends. If you have something, I don't know, extra high dimension, I don't know, like over like 100 dimensions or something, sometimes the random scan can help. But it's just, you're still like picking at random. So, yeah. So this is your normal one. Okay, yeah, and then the random scan is basically doing the same thing, except you're just randomly selecting which value to sample for. Okay. All right. Are there questions on this? Okay. So then I'll just really quickly. So you've got the random scan, and I'm not sure. Yeah. Random scan Gibbs sampling. Okay, pretty much the same. Just it's very similar. Very similar to systematic scan. Okay, except what you do is you just randomly select one of the dimensions D. Okay, then you condition the distribution on all other variables. Okay, and so you'll have x sub I for time t plus 1 coming from the distribution condition here, and yeah, basically using yeah, conditioned on all other variables. Variables kind of using their most recent value. Okay, is this okay? Yes.
Once you have like selected one from one of the D dimensions, is that taken out of the random selection until you select the whole, or is it?
It's technically not, but so yeah, so you can end up selecting the same variable twice in a row, and then your conditional would remain the same. Okay, I guess we'll look at like maybe a small example here. There's an example in the textbook that covers the beta distribution. I'll look at I'll show you maybe for a bivariate normal, and then we'll see how far we get in the math here. Yeah, and then on Friday we'll continue this on. Okay. So the Gibbs sampler. Well, I guess before I go on, we will go back to kind of Bayesian inference, and we will look at something called hierarchical models. Okay. So maybe I'll just talk a little bit about that. So I don't if you remember in the homework, there was we said the prior distribution for the baseball players was a beta distribution with parameters like 881 versus and 219 or something like that, right? And a lot of you guys felt like, where did these numbers come from? It really feels arbitrary. And I just said, oh, we looked at this blog, and the guy who wrote the blog said, let's use these numbers 81 and 219. And the reasoning behind it was just kind of like, oh, when we select 81 and 219, the shape of the beta distribution looks like this, which seems to kind of match our prior knowledge of baseball. And I kind of left it at that, right? In a hierarchical model, and I'll talk more about this in the coming lectures. In a hierarchical model, you say, well, you know what? I'm not comfortable saying 81 and 219. I want to say the value 81 is really a random value itself. It's some unknown value that, maybe is around 81, but maybe it's bigger, maybe it's smaller. Same thing for 219, okay? And so when you create your prior distribution, you're saying, we selected these parameters to define the beta distribution, or we selected these parameters to define the normal distribution that I'm using for my prior, and I'm not comfortable designating these prior parameters all by myself. So you know what? I'm going to say they themselves are random values, and maybe we can use the data to help us assist in figuring out what these prior values should be, okay? And so you can think of kind of now we're adding like another layer of random valueness, right? And that's why we're starting to call them hyper, what did I say? Hierarchical models. Thank you. Yeah. So we're setting up these hierarchical models, and then the prior distribution had these parameters, and then if we're setting something above that, they're called hyperparameters, and you know, you could build turtles all the way down and have like hyper parameters, and it just keeps going crazy. And then, you know, maybe at some point you say, well, maybe we should stop. But yeah, we'll look at this, and so in those situations, your model ends up being very much very high dimensional, because now you have parameters at all sorts of levels. But because there's a clear hierarchy, the relationship between the conditional distributions is made clear. And that's why something like Gibbs sampling works very well for those, because figuring out the conditional distributions does require a little bit of math, but it's not really hard math because of the hierarchical nature of the model. Okay? I've just been talking, but we are going to run out of time. We'll take a look at some of this stuff. Okay. I got 4 minutes left. All right. Well, I'll start it, and then we'll finish the bivariate normal example. Bivariate normal. Okay, and it says bivariate normal target distribution. So this is, we already have ways, we already talked about how to sample from this, right? So it's silly to use Gibbs sampling because we already know how to do this, but we're going to force ourselves to use Gibbs sampling to kind of illustrate this, right? So so our target will be two-dimensional normal distribution. Let's say we'll have mean 0, and then our my sigma matrix will be this. Okay, so there's kind of a correlation or covariance of rho between x1 and x2. Okay, so we'll say our x vector comes from this, and that's our target, and so our target PDF and I think this is correct. 1 over 2 pi times 1 minus rho squared, and e raised to this whole thing of minus x1 squared minus 2 rho x1 x2 plus x2 squared divided by 2 times 1 minus rho squared. Okay, so you can basically, if you look up multivariate normal, oh, I forgot, I should close this. Okay. Okay, so this is the PDF, and it looks scary because they write determinant 2 pi sigma, but you know, the determinant of a two-dimensional is, you know, so you can verify is this minus this, right? And it's the square root e to this, and it is. Okay, so that's going to be our target PDF, and we will use Gibbs sampling, and I've run out of time. But basically what we're going to do is we will to do Gibbs sampling, okay, we will need to find the conditional distributions. Okay, so we'll have the probability of x1 given x2, and also probability of x2 given x1. Okay, so basically in those cases we're going to just lock in one of those values and figure out what the conditional distribution is there. Okay, well we'll stop here, and then I guess we'll finish this up on Friday, and then I'll start talking hierarchical models and how all of this works, kind of.